right, action. Here we go. So I had a question about assignment 10, question 4. I'm just saying it so I remember to, maybe what I'll do is I'll put together some solutions to a version of it, and then I'll post those, help you along, because we don't have time to do it in class. I wish we could, but we're starting the fun stuff today, and I can't wait. Just a quick note though before we do. For assignment 9, I did have a couple people reach out and say, I'm doing the same thing and it's marking it wrong and I don't know why. And I said, don't worry about it. I'm just going to go back and look at the coding, and it's possible that they're just not rounding the Z scores. And then I didn't do it. So I still have to do that. So if you're feeling good about what you're submitting, just leave it as is, and then I'll change the coding. I suspect that they're just not using a rounded Z score, whereas we have to round to use the table. And so that would be the problem. And so just leave it, and it'll just regrade it and fix it, okay? And so my apologies, that's not fun when you're dealing with that. But I'll go in and fix it. Okay, let's see here. Today, test 1, I was so close to finishing the marking and I would have been a total hero, but I didn't. Wah, wah. I only have 2 more long answers to mark, and I saved the multiple choice for last. It's like, so this is section 5.1, and today we finally get to start with what I would truly call statistics. Everything else has just been developing some skills that we're going to be relying on, more or less. Some you'll forget completely. That's totally fine. And some we're going to build on a lot. So the normal distribution is one of those that we're going to build on a lot. Finding areas under the curve, finding probabilities. That's what we're going to be building on. Okay. And so chapter 5 does like an introduction to inference. Okay. And so inference is this general term that we use when we're trying to use sample information to infer something about the population. Okay. And so in general, it's using sample information to infer something about the population. So inference is where we're going to be spending the remainder of the term. And what's really nice now is, although it's super, I'm not going to say, maybe not overwhelming, but there's a lot of things to keep straight in that we introduce in chapter 5. But what happens is then we just keep building on that now, whereas before it was like, here's a little bit of this and a little bit of that and a little bit of this, and it was all over the place. Now, once you've got this this foundation, we just build on that and we introduce different types of questions that we could answer. Okay. And so today we just kind of take a deep breath and calm down a little bit. And we still have a lot of things to say, but we're going to be doing the same thing over and over and over again. Okay. And that's inference. Not the doing it over and over again, but just for different types of questions. Okay. And so where we're starting in chapter 5, is we're going to start with the first type of question. And I'm going to emphasize that there are different types of questions, okay? And because that's going to help you figure out where to go on your formula sheet, for example, right? And then how do you tackle the problem? What do you have to do? Okay, and so the first type of question that we're going to talk about is, so the first type of question is one sample proportion. So I've collected a sample, and now I have this sample proportion, which a sample proportion, I'm going to be using p hat is the sample proportion. And we'll see examples instead of not a phantom knock. Okay, so we're going to have this sample proportion. So I collected a random sample, and I found that 30 out of 40 dentists recommend Colgate. I don't know, who cares, right? And so that would be a proportion, okay? And so, for example, p hat might be 30 out of 40 dentists, blah, 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 recommend Colgate, Crest, who cares, right? And so that's going to be a sample proportion. Now, that's only out of 40 dentists, right? That's just a sample. What are we trying to infer? We're trying to use this sample proportion to infer, right, that applies to the entire population of dentists, right? And so our goal, let's see here, and maybe I'll use green here. We use this to infer what the population proportion of dentists I'm avoiding recommend, but is it 2 C's, 1 C, 2 M's? There. Whenever I don't know how to spell anything, I just work around it, or try to, or I just make it look really small and weird. There. Okay. So before we can do that, there are a couple of just theoretical things that we need to talk about before we're able to figure out, well, how can I take this sample proportion to learn about what the overall population is going to look like, right? Okay, so for us, right, what we said was that we're often interested in these population parameters, right? The P and the P goes together. That's from way back when, right? A population parameter. So a parameter is a measurement from the population, whereas a statistic is a measurement from the sample, right? S and S go together. And dink, dink. Okay. Often it's impossible to collect the entire population. Even if you wanted to, you can't, or it's too expensive. And so what's nice is we don't need to, okay? And so we use these sample statistics as point estimates, okay? And that's my best guess at what the population proportion is, okay? So here, the point estimate is my best guess for the unknown population parameters of interest. One of the issues is that, okay, if we collected a different random sample of 40 dentists, we would expect a slightly different proportion, right? It could be 31 out of 40, 32 out of 40, 29 out of 40, right? And so we expect some variability from sample to sample to sample. And so that's what statistics is all about, is figuring out, okay, so I've got this best guess, right? But then I also understand that if I just took a new sample, it would change a little bit. So now there's variability around this estimate. And so that's what we're working towards, is quantifying that variability. And so quantifying how sample statistics vary provides a way to estimate the margin of error. And you've probably seen, I mean, it's already highlighted, but I'll highlight it more. Seen margin of error or heard it somewhere along the way, right? And so a margin of error is kind of this buffer. Okay? And so one of the ways that I kind of describe the margin of error is as a buffer. So kind of as a, I'll put it over here. I think of it as a buffer, right? So now I've got this kind of width on my point estimate. Now, if I asked you something like, and we use margin of errors just kind of intuitively, right? If I asked you, how far is it to your house from this exact point, right? So I don't know, 4 kilometers. Thinking about me here. So I'm just downtown, I don't know, 4 or 5 kilometers. I'll say 4.5, right? That's my point estimate. That's my best guess. And then I would say something like plus or minus 500 meters. I'm feeling pretty confident in my point estimate. And so I built this buffer around, and we all understand that, okay, it's somewhere between 4 and 5 kilometers to her house, right? And so there is a true distance to my house, right? And so that's the population parameter that we're trying to guess, but we don't know what it is, and we don't need to know what it is, right? But we always start with this, my best guess, and then we build a buffer around it. Okay? And we go down a little, up a little, and then we're happy. Okay? It's that down a little, up a little that we need the math for, right? Okay, so if we think about, I randomly sample 1,000 adults from each state in the US, would you expect the sample means of their heights to be the same, somewhat different, or very different, right? The means from each state, right? So now I have a new sample of means, right? If you think about it in a spreadsheet, each state, right, you've calculated the mean, and now you're recording the mean from each state. Okay? So in terms of your spreadsheet, you might have something that looks like this, the mean and the state, right? Now I'm blanking. Washington, Oregon, and I guess I could have done California. Can't think of any more states. And so let's say there's some mean height here. So X bar Washington, X bar Oregon, because I don't want to think about actual numbers, right? X bar just indicates that that's a sample mean, right? Anything with a bar over it is a sample mean. And so here's the mean from Washington, here's the mean from Oregon, and so on and so forth. But what happens here is now you have a sample of means. A sample of means. You expect all these to be pretty much the same, right? All these heights, these average heights, because you're expecting averages to be close to what? You're expecting the average height from each state to be centered around the population height, average height, right? And so these guys are all to be the same, or roughly the same, right? Centered around the population mean height. Centered around the population mean height. Now there's a kind of a big example, but all it's leading to is showing you just an article where they include point estimates and the margin of error and how we deal with that. Okay, and rewind. Okay, so I'm just going to read the highlighted parts. You're welcome to read the rest if you want to, but so many words. So a plurality of the public, so wordy, 41% believes young adults rather than middle-aged or older adults are having the toughest time in today's economy. And so it goes on to talk about that, of course. And then here's where we get into some statistics, measurements from the sample. Among all 18 to 34-year-olds, fully half, that bothers me because it's not fully half, 49%. I don't know. I don't like that. Fully half, but 49%, no. Say that they've taken a job they didn't want just to pay the bills, with 24% saying they've taken an unpaid job to gain work experience. So now we have some sample proportions, right? Proportions are percentages, are probabilities, right? All those 3 P's, right? It's hard to see the connection to probabilities here, right? But the probability that a randomly sampled 18 to 34-year-old has taken a job just to pay the bills is 49%, 0.49, right? But we've left that in the dust. But what we are given here is that the sample proportion, and I'll just write bills here just to kind of indicate what one I'm talking about, right? They've taken a job that they didn't want just to pay the bills is 0.49, right? So now I have this sample proportion of 18 to 34-year-olds that have taken a job just to pay the bills. Yeah. We were also given another proportion, I'll call it experience or something. The sample proportion of those that have taken a job or an unpaid job for work experience is 0.24. Remembering that proportions have to be between 0 and 1, right? So we report them as percentages, but then we convert them to decimals as soon as we can. Okay. And there are more sample proportions in here, right? But on the next page, they introduce the margin of error. So often in a report, they have to tell you how they collected the data. That's where you determine if it was randomly sampled, right? If it's a good representation of the population, etc. So that's what they're doing here. Blah, 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 blah. Landline, cell phones, the usual. And then they finish with the margin of sampling error is plus minus 2.9 percentage points for results based on the total sample, okay, and 4.4 percentage points for adults aged 18 to 34. So they're kind of 2 subgroups, right? We've got the total sample, they have a margin of error of 2.9%, and then the subgroup of 18 to 34-year-olds, which is the one that we're kind of more interested in this case, had a margin of error of 4.4 percentage points, okay? And that's at the 95% confidence level. Stab in the dark here. What would you say? Now we're gonna get there, but I think it's good to introduce it here. 95% sounds familiar, right? what if I could do something like the 68, 95, 99.7 rule? That's exactly where we're heading, right? And so I've moved out 2 standard deviations, which are going to turn into standard errors, confusingly, away from the center, right? And so here, all I want you to think about here is just from the center, which I'm not going to denote in this case, 95% is between a Z of -2 and a Z of +2, roughly. Right? That much we know. Whoa, I didn't think that would come back like that. Well, it will. Okay, so for us, I think the ones we highlighted, so the proportion that with the bills and the proportion for experience, that was among all 18 to 34-year-olds. So for us, the margin of error for these guys, for these sample proportions, is going to be the 4.4. Okay. But I think there was one, where is that 41% here? A plurality of the public, which is everyone in the sample, right? That's an estimate from the entire sample. And so then the margin of error on those guys is going to be plus minus 2.9%. Yeah. And with the 95% confidence level, okay, even though we haven't really talked about it yet, we can say, okay, well, we're 95% confident that 41 minus 2.9, right, 38.1 to 41 plus 2.9, 43.9 of the public believe young adults rather than middle-aged or older adults are having the toughest time in today's economy. Okay, and so that's just rewording what they said as an estimate with bounds on it. Okay. And then same thing, right? Here we're 95% confident that 44.6 to 53.4% of 18 to 34-year-olds have taken a job they didn't want just to pay the bills. Okay. These are going to be called confidence intervals once we introduce them officially. Yeah. As an example, suppose the proportion of American adults who support the expansion of solar energy is 0.88. Now, when there's no hat on here, what this is saying is that we're pretending to know the population proportion, okay, which is not very reasonable. Why? If I had the population proportion, why would I be trying to guess what the population proportion is? You can just look at it, right? And so here, this is the population proportion, right? So just the P, and maybe a little bit irksome, because at the beginning of the course, I said anything that's from a sample is going to be using regular letters, let's call them, and then anything from a population has Greek letters. And then now I have a population proportion that's just using P. If you want, you can use pi, but pi gets kind of confusing, right? Pi is P, but it's also a constant, so it kind of makes it hard to read. So that's why we switched to P. But in general, we use a Greek letter for anything from the population. Okay. So now, if we know the population proportion is 0.88, right? Is a randomly selected American adult more or less likely to support the expansion of solar energy, right? What are we saying with the 0.88? We're saying the probability of someone supporting it is 88%. So you just randomly select someone, then they are most likely in favor of it, right? Because you're expecting the entire population proportion to be 0.88. So they are more likely, I guess I can just highlight the more likely to support, right? Since the population proportion is 0.88. All kinds of, but there was another one. Oh, whatever. Oh, there it is. Population. Suppose that you don't have access to the population of all American adults. That's perfectly reasonable. Right? Then in order to estimate the proportion of American adults who support solar power expansion, then you might sample from the population. So randomly sample from the population, ask them their opinion. Do you support it or not? And then use your sample proportion as the best guess for this unknown population proportion, right? So then your sample proportion is your p hat. So I've got this example, but don't be turned off when we go to the next slide that looks like that. I included it just for fun, but you can ignore it. Okay, so the idea is this. Each of you, right, you sample with replacement 1,000 American adults from the population. So you each go out and you sample 1,000 American adults. That's no small task, right? I'm making all of you do it, right? And record whether they support solar power or not. I'll just, there. Then you'll each have your own sample, yeah? Which means that you can find some proportion, right? 800 out of 1,000 were in favor of the solar power expansion, right? 810 out of 1,000. You each have 1,000, so you've got these different proportions, sample proportions out of 1,000, right, that are going to be in support of the expansion. So you're going to find the sample proportion. We did that. Then, if I ask you each to report your sample proportion to me, so I ignore all the samples, I just want all your sample proportions. Now I have a sample of sample proportions, right? And so now, another typo, right? Now I can look at the distribution of these sample proportions from the class. And you can do this in R. So here, maybe it'd be fun to do this in Excel for the lab next week. I'm on the hunt for lab ideas. I had a good one for this week, but it came to me too late. So I'll save it for next term. It was one of those, I woke up in the morning, oh, I can have them do this. It's too late. So it's just an itty bitty lab this week. So what we would get if we looked at the distribution of all those sample proportions that we've collected, right? I said, get me your sample proportion. All right, so that I can make this beautiful histogram. What does this look like? Wow, this looks familiar. Feels good, right? Whee! Right? We know how to deal with that, right? We know how to find probabilities associated with this. We know how to do stuff with a normal distribution, right? And so that's kind of a fun thing to go from essentially a categorical variable. It is a categorical variable. Do you support it or not, right? And then all of a sudden you collect enough samples, now you have a normal distribution, right? That's crazy. And so I guess it's on the next page. I gave it away already. What's the shape of the distribution? It looks approximately normal, right? And so it looks symmetric and bell-shaped, which I'm going to call a normal distribution. Statisticians don't like to commit to anything, so we always say approximately normal. I said approximately. Yeah. What's another kind of interesting thing when we think about the center? The center, if we kind of drape a blanket over this thing and we think about the peak, what's very interesting and a fact is that it's going to be centered on the population proportion, which if you take a step back, it makes sense, right? We expect our sample proportions to be close to the population, right? You don't have something once you've looked at a sample and you've taken the sample proportion of it, it should be roughly the same as the population. So they're all huddling around the population proportion. And so that's what we're seeing here, right? We're seeing this normal distribution centered on the population proportion. Oops. So that's something that is hopefully helpful in remembering that you are going to have variation, right? Variation in your sample proportion. Now you could have a sample proportion that's down here in the tails, right? And not know it because you're only going to collect one sample. You've done your best to collect a random sample and you've checked all these boxes and for all you know, your sample is perfectly representative of the population. What we don't know is where it would fall on this number line, right? You could just have a fluke random sample that is somewhere down here in the tails, okay? And so that's where the uncertainty comes in. And so we assume that we're hanging out around here in the center, but we actually don't know because we only collect one sample. Okay? And it's coming from this sampling distribution, which is the collection of all the possible samples. Okay? I'll write that here. It's the collection of possible samples. Okay. So in real world applications, we never actually observe the sampling distribution, but we do have established sampling distributions that we refer to. Okay. And so where they come from are the central limit theorem. Now, the central limit theorem is just as important as it sounds. Okay. And so it's what allows us to use the normal distribution for quantifying the variability around a sample proportion, for example. Okay. Well, that was a lot of words. Let's take it back. So sample proportions will be nearly normally distributed with a mean equal to the population proportion. And then we introduce this standard error. The standard error is a measure of spread, okay? But the standard error, so here it's spread, and I'll write it up here. The standard error is the standard deviation, right? That's a measure of spread. It's the standard deviation of the sample statistic. kind of redundant to say sample statistic, but I'm just emphasizing that a statistic is from the sample. Okay? And so it's just a matter of terminology. It still behaves the same as the standard deviation, okay, because it's the standard deviation of the sample statistic, in this case, the sample proportion. And so here, this is the standard deviation of p hat. But because that's really long to say, we swap it out and just call it the standard error. So that's going to be the spread around p hat. Okay. And from the 68, 95, 99.7 rule, which we can use because we have a normal distribution, right? We know that we can fit roughly 3 standard errors underneath the curve before the area gets super, super small, right? So what we say is p hat follows a normal distribution, right, with a mean of p and a standard error of the square root of p times 1 minus p over n, which I often write q, right? 1 minus p is q. But here, the standard error behaves as the standard deviation did before for us, right? So this behaves like the standard deviation. Yeah. In the sense that we can fit 3 standard errors under the curve, right? So if we're centered on p, we've got a normal distribution centered on p, and then I can go p minus the standard 1 standard error, p minus 2 standard errors. I did not give myself enough space here. P minus 3 standard errors. Yeah.
When we were using the standard deviation for the sample, we were using n minus 1. We're using n now as the divisor because it's the population that we're talking about.
Yeah, sort of. It's that's beyond our scope. What I would say is we just accept this as fact. Cool. Okay. One of the problems though is, well, we just said I don't know what p is. We're trying to guess what it is, right? So that's one of the problems that we have. But luckily, I have something to step in, right? I have my sample proportion. That's my best guess. And so what happens is, and I've got it somewhere here, but it's way too far. I'll scroll back up, but I don't want to write it because that slide is getting very cramped here. But we don't know what p is, right? But besides that, there's not a lot of information that I need here. That's nice, right? P and then P again and then N, and that's it, okay? And so what we do is we substitute P hat instead of P, okay? But knowing that, let's go back up and say that here, okay? So here, when we're working with these problems, okay, we're going to be using a standard error of the square root of p hat times 1 minus p hat over n. Okay? If you kind of dissect the standard error, what happens as n increases? So as I increase my sample size, what's going to happen? Then I'm dividing by a bigger number, which makes this whole fraction smaller. A square root of a smaller number is still smaller. right? And so as I increase my sample size, the spread, which is the standard error, the spread is going to tighten up around my population proportion, right? And so that's why we have it ingrained, right? Oh, a larger sample size, increase your sample size, bigger sample sizes are better, right? And that's because your estimate for the spread gets tighter and tighter and tighter around the population, which also makes sense, right? If you think about it in the way that, okay, you're sampling from a population, the more of the population that I'm sampling, the closer I should be getting to the actual population, right? Should be increasing towards that population proportion. So here, so as n increases, samples will yield more consistent p-hats, which means that the variability or the spread or the standard error among the p-hats will be lower. We do have conditions that have to be satisfied in order for us to use the normal distribution, which we saw before, right? I gave you a bonus opportunity, right, to study for. And one of the conditions that we saw in order to use the normal approximation to the binomial, which is very similar to this, is you have to see at least 10 successes and at least 10 failures, right? And we're gonna have the same conditions here. So in order for the central limit theorem to apply, the sampled observations have to be independent of each other. That's just a fact. One of the main ways that we do that is by random sampling, right? Then I can assume that they're all independent of each other. And this one, I don't check as often, but if sampling without replacement, then n has to be less than 10% of the population, which is kind of counterintuitive. We just said we want large sample sizes, but not too large. Why? Because if I have a sample size that's larger than 10% of the population, all of a sudden, I'm introducing observations that might be dependent on each other just by random sampling. And so that's the problem. This one, I rarely check this one. Because for us, as long as the sample size is big enough, then we're happy, right? We never have to worry about having too large of a sample. That seems really kind of cushy. So I rarely check that one. So the one that I check is, was the sample randomly sampled? Then I can assume independence. In terms of the sample size, there should be at least 10 expected successes and at least 10 expected failures in the observed sample. Okay. Now, that's really hard to verify, right? If we don't know the population proportion. Okay. And so what we check is we look for the number of observed successes and failures to be at least 10. What's that going to look like? In terms of the math, that means that you want to make sure that n times p hat is greater than or equal to 10, and n times q hat is greater than or equal to 10, right? Where q hat has the same relationship as q, right? 1 minus p hat if you want a q hat. It's also possible that you might have the number of successes just given to you in the problem, okay? And so the other option is, or x is greater than 10 and n minus x is greater than or equal to 10, where x is the number of successes. Right, if I tell you 31 out of 40 dentists recommend Colgate, then I have 31 successes. I don't need to do the 31 over 40 to find that decimal and then multiply it by 40, because then I'm just canceling out to get to 31 anyways. But this will always work, but here's a shortcut if you want it. If you have X. Okay, so now we're back to that slide that I skipped to before. So we're trying to use P. We don't know what it is. We're trying to figure out what it might be, what a reasonable range for P might be. And so what we do is we just substitute P hat for P. So the standard error is P hat times 1 minus P hat over N, which, if you're lazy like me, P hat Q hat over N. And then don't forget that square root. So that's what we're going to use as our standard error. Okay, so that's our standard deviation stand-in. So many stands. This one's just kind of for fun, right? What if that condition isn't met? The number of successes greater than 10, the number of failures greater than 10. That's not hard to achieve. You have to have a minimum sample size of 20, right? Depending on what your proportion is. And so here, I just want to show you what it looks like, but not spend too much time on it. So the probability or the proportion of successes is 0.1. So if I have a sample size of 10, it looks quite skewed, right? And then if as I increase to 25, it still looks quite skewed, but at 50, or I'm happy with that, but at 50, it starts to look very normal to me, right? And so as you increase your sample size, you approach this this normal distribution. Okay. And I'll let you read those, but they're just for fun. Now we're ready for the confidence intervals for a proportion. And so just as a heads up, what we're going to be doing, this is section 5.2. In 5.3, we introduce hypothesis testing. And together they make inference. There are a couple of other things that we can do, but at its core, we can split inference into confidence intervals, hypothesis testing. And that's what we're going to be doing for all these different types of problems. Is that for me? No? All these phantom doors I'm hearing. So we'll start with confidence intervals today, and then we're introducing hypothesis testing on Monday. All right. So like I said, intuitively, we use confidence intervals just by default, right? I have some best guess, I put on some buffer bounds, and then I have a confidence interval, okay? And so a plausible range of values for the population parameter is called a confidence interval. Notice that this is very big, right? The population parameter, and that's because this is going to change. Depends on the question. For now, the only population parameter that we're going to be dealing with is the population proportion. But then we quickly move into what's the difference between two proportions, right? Now I have two samples and I want to compare their proportions, right? And then we move into means. Now I have one sample mean, and then I have two samples, and I want to look at the difference between the two, right? And so we're just going to build on different scenarios. But in general, right, a plausible range of the values for the population parameter, that's what a confidence interval is. Okay. And so the common example is, well, using a sample statistic, so that's your best guess, right? Your point estimate. To estimate a parameter is like fishing in a murky lake with a spear, and using a confidence interval is like fishing with a net. Okay. And so you can't see anything, much like the population, right? We don't know what it is. We know it exists. But if I just use my spear, my sample proportion, I'm not going to catch the fish. It's very unlikely, right, that is the fish. But if I use a net, then I'm more likely to have captured the fish or the population proportion in this case. Okay. Oh, it's so long. Okay, Facebook categorization of user interests. So most commercial websites collect data about their users' behavior and use these data to deliver targeted content. Haven't noticed. Recommendations and ads to understand whether Americans think their lives line up with how the algorithm-driven classification systems categorize them. Pew Research, which is a big Pew research firm, asked a representative sample of 850 American Facebook users how accurately they feel the list of categories Facebook has listed for them on their page, blah, 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 blah. How well does it match what your actual interests are, right? So basically, how good is their algorithm at predicting what you like? Pretty good, I'd say, for my case, but I'm pretty basic, I guess. 67% of the respondents, so of the respondents telling me that this is a sample proportion, right, said that the listed categories were accurate. Like, yeah, you got me. Yep, I do want to buy all those things. We want to estimate the true proportion of American Facebook users who think the Facebook categorizes, that's a weird sentence, categorizes their interests accurately. So here, first thing we pointed out is of the respondents, tells me right away that this is a sample proportion, and that sample proportion is 0.67. Okay. Now, before I do this, let me add a page here. Get some lines so I don't write all over the place there. So we said that my sample proportion was 0.67. What was my sample size? Are we told what the sample size is? 850, nice. Okay, that's good. Using that, how many successes did I have, right? So if X is the number of successes, should be 67% of 850. Let's do that. X is 850 times 0.67. $569.5. That can't be, but that's okay. They've rounded the p hat, but that's okay. All right. Okay. So what we want to do is we want to estimate the true proportion of Facebook users who think that these categories are accurate. And so what I have is I'm going to start with my p hat, and I want to go down a little and up a little. We'll see how much, right? Let's do this. So I've got my p hat here. I know that these proportions, and maybe I should draw these in the opposite order so that it looks better. So now I've got my p hat in the center. To my knowledge, right? It's a good estimate of what the population proportion is. And we also know that the standard error is p hat. Can I do q hat? Save us some writing. Q hat over n. What's really fun is we have all these components, right? And so here the standard error is going to be the square root of 0.67 times 1 minus 0.67, oops, 0.33 divided by 850. So if I do that, divided by 850, and then don't forget that square root, I get roughly 0.016, 128, blah, blah, blah. Okay. That's going to take the place of the standard deviation from before, right? And so here, you can think of this, I'm going to put quotes around it because it's the standard error now. We've got a new term, but it's going to behave like the standard deviation. Now, let's see here. If I want to go from p hat, which was 0.67, and I want to go and be 95% confident, then I'm going to stretch this out to cover 95% of the curve. Okay. So at some point here and some point here, I'm going to have these bounds, right? A lower bound and an upper bound of my interval. Okay. So how am I going to do that? I would do p hat minus, right? 68, 95, so 2 standard errors now, times the standard error of p hat, which we already calculated to be 0.016. And then I'm going to go up 2 standard errors. So here I have p hat plus 2 times the standard error of p hat. And you know what? I'll be proper. Put a little standard error of p hat. So a little subscript p hat, only because later we're going to have standard errors from different things. So I should be proper about it. Okay. So I can summarize this as p hat plus minus, which we already saw from that article in the beginning, right? Plus minus 2 times the standard error of p hat. We said this plus minus is the margin of error, which is true. Okay. And so now, what can I do? What can you do when you live in a shoe? 0.67 plus minus 2 times 0.016, because we already did the math. Now, if I do 2 times 0.016, I get plus minus 0.032. 0.67 plus minus 0.032. We always write these as an interval. And so to write this interval, you start with a round bracket, and then you do your lower bound first. And I'm going to be super picky about that because the interval from 4 to 2 doesn't exist. There is an interval from 2 to 4, right? So you always have to write them from smallest to largest. And so you go 0.67 minus 0.032 puts me at 0.638, comma, up to 0.67 plus 0.032, whoops. I get 0.702, end bracket. Okay? And so you must write from smallest to largest. Otherwise, what you're trying to tell me doesn't exist, so it cannot be true. I'm picky like that. Yeah. Okay. So, all right. What does this mean? We built a 95% confidence interval because we moved out 2 standard errors from the sample proportion. And so now what we can do is we can write this as a sentence. And I would encourage you to always follow this, the interpretation format until you're comfortable. So it goes a little something like this. We are 95% confident the interval from 0.638 to 0.702, just grabbing the values that you just found, captures, right? Remember, you're fishing with a net, right? And so captures the population proportion of adults who think that the Facebook categories are accurate, right? And what am I doing? I'm just grabbing the question and rephrasing it as an answer. Estimate the true proportion of American Facebook users who think that Facebook categorizes their interests accurately. I could even say captures the true proportion here. Let's do that. Captures the, can I be so bold and say, well, scratch this, captures the, I don't need this the anymore. The true proportion of American Facebook users who think the Facebook categorizes their interests accurately. So many typos in this section. What was she doing? Got busy, I think. Midterm time. All right. So here, right, the only thing that you really need to memorize is we built some 95% confidence interval, and we found the interval, right? And captures, and then you just reword the question as an answer, right? And so here, the true population is telling you the population proportion, or the true proportion is the population proportion, right? We're trying to use the sample proportion. We did that and built the interval around it. And now we're trying to capture the population proportion. If we wanted to change this confidence level, what would we have to do? I'll add another page. Need a little bit more. We can change the confidence level if we had p hat plus minus 2 times the standard error of p hat. What would we have to do? Well, this 2 is what gave us that 95%, right? 2 is for 95%. So we can replace that 2 with a generic Z star, right? Z, because we moved out 2 standard errors, right? And so we replace 2 with a generic Z star. So what we can do is we can find any confidence interval, right, at any confidence level. Okay. This 95% is the confidence level. I'll say that confidence level. So if I want to make any confidence level, right, then I'm going to go down to a negative Z star and up to a positive Z star. Okay, so now I can rewrite this as P hat plus minus Z star times the standard error of P hat. Or if you prefer, the square root of P hat Q hat over N. But I'm skipping that. Okay. Z star, you can use your Z table to find it, right? And so let's do what is Z star for a 90% confidence level? Remember I said everything that we learned so far, a lot of things, especially stuff regarding the normal distribution, we're going to use. And if we start here, Z is centered on 0. And what I'm going to do is I'm going to force this area to be 90%, right, or 0.9. Which means that I have 10% left over, but it's evenly spread out in the tails, right? Which means that I have 0.05 here and 0.05 here. If I can find this negative Z star by symmetry, because it has to be the central 90%, I also have the positive Z star, which makes sense. That's where the plus minus came from in our formula. Okay. And so now I can go to, we know how to solve this, right? I can find the table entry closest to 0.05 and I can map it back to the Z that makes that happen. So let's see here. Do I have the tables? So I'm searching, and I'm trying to find some Z close to, I'm choosing between, where were they? Here and here, right? Looks like it's even. So I just choose one or some value in the middle. That's sneaky. But what does this map back to? It maps back to negative 1.6 and then somewhere here, right? That never happens where we've got an even distance on either side. And so I'm going to use 1.645 because I'll give you a cheater way to find it. Do you want the cheater way now? Maybe. It involves a new table. Fine, just a sneak preview of the T table. This is the T table, slightly different. We could have only used the T table. Notice all we care about for now, well, not the degrees of freedom, is we've got these confidence levels up top. And if I want a 90% confidence level, just ignore everything in the sandwich until down here at the bottom, you've got a Z star. Oh, that's nice. Oh, cheat codes. Well, not really. But here, so, whoa, what happened? Don't know what that was. Where'd my pointer go? There. So here, this is how I know that Z star is 1.645. So you could go through and use the Z table and backtrack and do all that. But here are the most common confidence levels that we use, right? And their corresponding Z stars. I did not bring the T-table because I didn't think I'd be doing it today, but I'll bring you T-tables on Monday, how about? Okay, and then you'll have them. But it's good to know where they came from, right? And so the table entry, I guess I should say using the Z table. The table entry closest to 0.05 is 0.0505 or 0.0495, corresponding to Z equal to 1.64 or Z equal to 1.65 respectively. That's too much work. I'm gonna say use, or I'll say I'm using Z star equal to 1.645, halfway between the two. Doesn't really work that way because I've got a slope, but that's fine. Such a small increment. So here, negative 1.645 and positive 1.645, right? Which means I have to move 1.645 standard errors away from p hat to capture the central 90%, right? 90% confidence level. Okay. If we go back to our cheat table, we said for a 95% confidence interval, we were using 2, right? But how about we go down here and, 1.96, that's so different from 2. Oh, wait, is it? Not really, right? It's just more specific, right? If we had used the Z table, we would have found 1.96, but it's approximately 2, right? I think we can all agree that that's approximately 2, right? So now, we can build a confidence interval. Whoa, why isn't that showing up? Has it been doing that before? It's showing up nice on my end. I don't know. Does the pointer show up? Yeah. Okay, fine. I'll just read it to you. Facebook's categorization of user interests. P hat 0.67, that's where we started. N is 850. You can't see it. That's weird. The approximate 95% confidence interval is defined as, see, I'm not making this stuff up. It's on here. Just not on here. Very confusing. So in general, we take our point estimate plus minus 1.96. Now we know where that came from, right? It's not just out of the blue, times the standard error of the point estimate. Okay. And we did this, we found the standard error of the point estimate, and then we found, did we find these intervals? I think so. So long ago. And we interpreted it. Nice. They rounded to 2 decimal places. So in terms of the interpretation, it's going to be really important how we interpret this. And so a couple of options are, we are 95% confident that 64 to 75% of American Facebook users in the sample, that's not true, right? We found a sample proportion and it was 0.67. So there's no range here, so it's not this one. 64 to 67% of all American Facebook users think Facebook categorizes their interests accurately. I think that one we'll keep it because I'm happy about this of all American Facebook users, because that's the key with these confidence intervals, is that they're capturing the population thing. So I'm going to parking lot that one. There's a 64 to 67% chance. Well, I'll stop you right there. It's not that one, because we're not talking about a chance. We're just talking about some interval that's trying to capture this thing that we can't see, right? And so right away, don't say that. And again, chance. No. So let's convince ourselves that this one is what we said. So we're 95% confident that, and then what we said in our blurb was that the interval from, let's say 0.64 to 0.67 captures the proportion, so we can convert those to percentages, that's fine, of all American Facebook users who think Facebook categorizes their interests accurately. So that is the one that we want. And I'm out of time, but I want to finish on the width of an interval. I had someone ask me, well, why don't we use 100% confidence interval? Well, because you would have to make your interval too wide. So taking a look at tomorrow's weather, the high temperature will be between minus 40 below, or 40 below zero and 200 above. This guy's never wrong, right? We're 100% confident, but it's not very useful. All right. With that, I release you. Have a great weekend. See you on Monday.